Thank you for the introduction. I want to thank the organizers for giving us this kind of opportunity. Sato from Fujitsu. I'd like to talk under the title Quantum Computing at Fujitsu. This is the outline of my talk. First, I explain the background of our research, then talk about quantum computing at Fujitsu. I also explain quantum-inspired technology, digital annealer. So this slide explains the history of computing technology at Fujitsu to solve social issues. We've been working on high-performance computing like Fugaku with the mainframe. But as you know, the end of Moore's law is approaching. Improvement of computing performance is slowing down. So around the world, there are activities to improve the performance with dedicated chips like AI chips. And so at Fujitsu, we are working on digital annealer, specialized in combinatorial optimization, and also we're working on R&D of quantum computing. So this past April, computing as a service vision was released. So HPC technology and digital annealer technology we own. So we want to integrate all of that. And we want to add a software layer and provide that as a service. We plan to start this autumn. In the future, quantum computing should be added. That is our vision. So I think you know quantum computing, there are some categories, Ising machine and the gate-based systems. So we have the annealing machine, the Ising machine. So Ising model we implement in CMOS circuit. That's the digital annealer that we've developed. With quantum gate-based systems, we're working on that as well. I'll explain later. We have the superconducting and diamond systems that we're working on. So first I talk about the quantum computing. So you've heard many times since this morning, what kind of problems are expected to be solved with this? Some of the problems difficult to solve by today's computers, like chemical computation. So that's difficult to do with classical computers to have an accurate solution. And so quantum computers should be strong with this kind of quantum mechanics. Also machine learning and finance and economy. There should be applications suited for quantum computing. And so it's difficult to solve quantum mechanics problems, but with quantum computers that will be solvable, and you might be able to find novel phenomena and principles. So this shows the current status and challenges of the gate-based system, and the number of qubits is one issue. So this shows the number of qubits finally has surpassed 100. But for a fault-tolerant system, you need 1 million qubits or more. So it's going to be a long road ahead. So for the time being, you want to focus on specific applications. So for limited applications, so it's the NISQ computer. And the error is a major impediment. So to mitigate or suppress error, that kind of technology is worked on. And also error correction is going to be important for error-tolerant computing system. So next page, I talk about our R&D strategy for quantum computing. So as we show from quantum device to application, we work on every layer. So difficult to do with just one company. So we collaborate with prominent research laboratories, RIKEN at the device layer, or TU Delft or Osaka University, and Kinesis and Keysight at the application layer. And we're focusing on software. And for the hardware, we don't know what the final solution is. So we're collaborating with multiple institutions and working on multiple technologies. most recent developments. So the application, what to use it for, is very important for companies. We don't have reliable quantum computers, so we developed a simulator. And so from this fiscal year, we're going to have a joint research, or we have started joint research with end users. And here I talk about our efforts for hardware. We work with Deacon, Dr. Nakamura, who demonstrated the quantum bit for the first time. And so we have the RIKEN RQC Fujitsu Collaboration Center established last year. And so we're working on hardware technologies and application development involving users. And we have a chip at our booth, so please take a look. And with DEFT, TU DEFT, we're working on a diamond system, as you may know. You can have a V center or tin or nitrogen, using that as a spin for quantum bit. Compared with a superconductor, it can operate at a higher temperature, 4K, so it could have a smaller fridge. And as was mentioned previously, you can connect with light between the qubits, so that could potentially lead to larger scale in the future. It's still emerging technology, just started, so we're working with TU Delft from basic research. And recently, so error correction was demonstrated using this technology. It was published in Nature. For software technology, we're working on various things. Of course, we're working on application as well, but error suppression, error control is quite important, we see. And so with quantum benchmark absorbed by Keysight from 3 years ago, we've been working on error control. And with Osaka University, Dr. Fuji with working on error correction software and software technology for logical computation. And our digital annealer is being used to detect errors. So we did a demonstration of that, and we published a paper on that reference as shown. And the most recent topic, we have the Fugaku technology. And using that technology, we've developed the world's fastest 36-qubit quantum simulator, and we did a press release this March. According to our research, compared with others, it's twice as fast. And utilizing this simulator, we're developing quantum applications. By September, this should be expanded further to 39 qubits. By end of this year, it should reach 40 qubits. So as I've been saying, using that simulator, we're developing applications. We want to be early in this field. And with Fujifilm, we put out a press release. So we're working on this in manufacturing and finance and computational chemistry with about 5 countries, including Fujifilm. And we're doing a lot of development at software level. And with Kinesis, from this fiscal year, we started joint research, so implementing their software on our system. And next year, with RIKEN, we're going to release the superconducting quantum computer, and in the future develop applications for them. So about the future, as I said, in September, we're going to release a 39-qubit quantum simulator. By end of year, reach 40 qubits. Next fiscal year says 100 qubits, so it will be less than 100 qubits. That will be 50, 60 qubits. And then that should be exceeding 100 qubits in 2024. And in 2026, we should have a quantum computer with larger than 1,000 qubits. with the diamond spin, we have a different roadmap, which we like to explain to you in a different opportunity, different occasion. Next, I talk about the digital annealer, which is a quantum-inspired technology. So quantum computing, it's not at the level that can solve practical problems, but digital annealers, 2018, 4 years ago, we started to provide a circuit. And in various fields, it's already being used in actual applications in business. So digital annealer strengths shown here in the summary page. So quantum computing, to apply it takes time, is what we thought. So 4 or 5 years ago, we started this kind of development. And 2018, we started providing this. And already a lot of customers have been utilizing this because of its technological superiority. So left-hand side, you see the characteristics of the technology. So hierarchical parallelization and constraints is used to limit the search space. So we have various technologies as part of this. And as a result of this, it's been accepted by many customers. We've put out many press releases, and I'll explain in more detail, in more concrete terms later. This is the roadmap of digital annealer. As I said, we started the service in 2018, started with 1,000 to 8,000 bits. It was a dedicated hardware implementation. And then last year, or 2 years ago, in 2020, third generation came out. So it was a hybrid solution architecture with hardware and the software can solve 100,000 qubit level problems. This past June, we released the fourth generation one, and the next page explains that in more detail. So convenience of the third generation is maintained, and so cost and constraint items can be entered separately from the third generation. In addition to that, with the fourth generation, we developed a large-scale annealing core using GPU. And so hitherto, we were able to solve 100,000 qubits, but you had to break them up. And now you don't need to do that. You don't need to fragment. And the constraints, you can enter that in software. The constraint conditions can be used at the hardware level to limit the search space to have higher speed. So this is the comparison with the benchmark. This is based on our research. That's a disclaimer. And D-Wave is the most famous quantum annealing. According to our research, it was about 5,000 qubits, and the number of connections limited. But the system based on CMOS, including ourselves, you can do 100,000 or a million bits, and it's full connection between the qubits. So our system, what's the biggest characteristic, uniqueness of it, and how is it superior to others? Well, we've been providing this 4 years from 2018, and there are many constraints in customers' problems. And how to handle that appropriately is quite important. So various constraint conditions can be handled. That's the strength of ours. And you can use that constraint to actually speed up the computation. That is the strength that we have. And from here, I'd like to talk about what kind of applications it is used for. This is the example of IT drug discovery. As you know, it's difficult to develop pharmaceutical, especially if you do it experimentally. So using computers is being employed in various places. But as you see in this example, you have these various candidates. And how does it combine with proteins has to be shown. And if you just use HPC, ordinary supercomputers, it takes a lot of time because it's difficult to simulate that. So we combine DA and HPC. So you do rough screening with DA. that reduces the amount of time you need on the HPC. That accelerates the process. And this is what we did with Pepti Dream. Amount of time used to take a week. That's now half a day. So we have speeded up this kind of process, and we want to apply this to drug discovery projects more broadly. Other use cases shown here with Melco Investments Inc. We work on financial portfolio optimization, and digital annealer is used for that. So that would be a huge amount of calculation in a classical system, but it can be now optimized in a very short period of time. And another example is logistics. We have worked with Toyota Systems Corporation. So optimization of a logistic network for parts. So of the 3 million or more routes, you can search for the best routes very speedily. And the 2.5% reduction in total logistic costs. It may sound small, but actually it's quite significant in the field of logistics. And with COVID, in terms of COVID, the rules have been relaxed. And last year in Germany, they wanted to put in spectators, but you wanted some social distance, but distance could be reduced for family members. So digital annealer was used to optimize the seating, and that increased the seating allocation. I think I'm going to end a bit early. Interesting example, optimization of spacecraft operation for space debris recovery. So in the past, it was manually calculated what the optimal route is. So we tried using digital annealer for this. Amount of time required was reduced substantially. And also, fuel consumption was reduced by 18%, operation time 25%. So digital annealer is being utilized by various clients. And so finally, to conclude, at Fujitsu, we're working to solve social problems in the future, and we're utilizing computing and quantum computing to solve social problems. And it will take time for quantum computing to become capable. But we're going to focus on basic research, and we're going to use quantum simulator as well to try to solve customers' problems from an early phase. So digital annealer, quantum-inspired technology, it's already in practical use. We have many use cases. So this, combined with HPC technology, we want to provide as computing as a service to solve customers' real issues. That concludes my talk. Thank you for your attention.